Hi everybody, it's Miss List, and I am here with the start of Unit 5, which is actually one of my favorite units, and it is on a topic in chemistry that we like to call kinetics. So when we talk about kinetics, we are talking about how fast a reaction is happening. So in 5.1, we are introducing the concept of a rate. So a rate is simply a change in something per unit time. So when you drive in your car, your miles per hour is a rate. It's miles, change in miles distance over unit of time, hours. In chemistry, though, we measure the rates of reactions. And so when we talk about a change in a substance, we're talking about measuring the mass, the volume, the moles, the molarity, any of those changes over a unit of time. The unit of time that we choose depends on the reaction. It can be anywhere from seconds to minutes to years even. Some half-life reactions take millions of years. And then the last thing we need to know about rates is we can only determine them experimentally. So you actually have to do the reaction in order to measure these. This is not something that we can predict. We have to study the experiment and the reaction and test all of this. The first thing we need to know about rates is that they change according to the balanced equation's coefficients. In this graph, I have some lines, and those lines represent the reaction N2O5 goes to NO2 gas plus oxygen gas. So we're looking at this reaction here. And we notice that our change in concentration over time for the reactant is decreasing, and that should make sense to us because it's getting used up. The other two are products, and so those start at 0 and are increasing. So O2 is being produced, as is NO2 being produced. Now, what I was talking about as far as the change based on their coefficients, if I look, I have 0.16 as my initial concentration for my reactant, and it goes down to 0. So if all of that gets used up, then I should be able to follow the stoichiometry to see how much of the products are produced. So if I start with 0.16 molar of N2O5 and use my balanced chemical reaction, it's 2 N2O5 for 4 NO2s. Well, that gives me 0.32. And if I go over here and look at where this graph stops, it is 0.32. And so it follows the reaction stoichiometry. If I did the same thing for my oxygen, if I started with 0.16 molar N2O5, it is 2 N2O5s for every 1 oxygen. And so this is actually going to be at a slower rate because of the stoichiometry of the reaction. And if we look, that matches up with my graph and to see how much O2 is produced. So again, that's what we mean when we say they change according to their coefficients in the balanced equation, is that we follow stoichiometry. Our first two examples explore that idea. It says consider the combustion of ethylene, and they give us the balanced equation. And it says that if the concentration of C2H4 is decreasing at the rate of 0.036 molar per second, what are the rates of change for CO2 and H2O? So I would do similar to what I was doing before. And if this is the rate for C2H4, I would go to the balanced chemical equation and see that C2H4 has no coefficient, which we assume is 1. And they're asking about CO2 has a coefficient of 2. So for the carbon dioxide, I should get twice as fast. The rate is going to be happening twice as fast. So I should get 0.072 molar per second for the CO2. Coincidentally, it is the same coefficient for the water, which is the other thing that they asked me for. So it's going to be 1 C2H4, and then the coefficient for water is also 2. This is just a coincidence that they have the same coefficient, but I'm going to get the same answer. And again, because of that coincidence, if it wasn't the same coefficient, we would not expect these to be appearing at the same rate. The reason I keep saying that these are appearing is because they're products. They are being made. Our reactant is decreasing at that rate because it's getting used up. All right, another example here says the rate of decrease of N2H4 in a closed reaction vessel is 74 torr per hour. So it's going to be 74 torr per hour. And that was for the N2H4. And they want to know about the appearance of NH3. So that's going to be my product that is being produced. So I go to the balanced equation, and it is 1 mole of N2H4 for 2 moles of NH3. So I am going to double that and get 148 torr per hour, and that is the appearance of NH3 as our product. The other thing that 2.1 introduces is the concept of different types of rate. And if you've had some physics, this should sound familiar to you. Usually, when we talk about rates, the average rate is what is being described. And so the average rate would be the rate over the entire time unit. So in this graph, I started at 10 and went down to 2. So that would be a change of 8 over 8 hours. And so that's going to be the average rate. Did it do that the entire time? No. But that is the average. And I like to use cars because cars is what a lot of people can relate to. So when I talk about the average rate, I'm looking, say I took a road trip to Florida. And depending on where you live, that might be close. But I'm in Tennessee, so a road trip to Florida is not is not close. So let's say I drive 600 miles and it takes me 8 hours. Well, that would be the average. It wasn't what I drove the whole time because I might have sped up and slowed down during that time. But over the whole course of the trip, that would be an average. And so when we talk about averages, we're talking beginning of the reaction and the end of the reaction. The initial rate, we look at it as the change in the very first unit of time. So for an initial rate, we would go from 0 to 1 hour and look at how much that changed. And from 0 to 1 hour, it went a change of 2 per 1 hour. So that's a different rate than what we see as the average rate. So the initial rate would just be for this beginning part, that first time unit. And then finally, we have what's called an instantaneous rate. And an instantaneous rate, I like to think of as when you get caught with a speed check radar. So this is an example of when someone is getting pulled over, the officer says, well, you were going 70. And what they mean is that 1 second that they checked you were going 70. But that wasn't what you're traveling the whole time. So instantaneous rate is not necessarily at the beginning, but it's over a small unit of time. And the example here is they might check the rate over a few hours instead of all the hours. So these are 3 different ways that we can look at rate: the total, which is average, the initial rate, which is just at the beginning, and then the instantaneous rate is over any small interval of time. The other part that we have to talk about for reactions is the concept of collision theory. So in order for a reaction to happen, 3 things have to take place. The reactants must collide, so there has to be collisions. They have to have proper orientation, and they have to have enough energy that will overcome the activation energy. And when we talk about orientation, we're talking about how the reactants are lined up with each other. So are they interacting this way? Or is the oxygen coming from this side? That actually matters when we talk about the mechanism that these reactions undergo. And so that's what we mean when we talk about, are the particles oriented correctly? Are the parts colliding that need to collide? So here are some factors that affect the rate of the reaction. So we can actually make reactions go faster or slower by controlling these things. And if you learned anything or focused on anything in, say, a first-year chem course, I know I cover these in my first-year chem course, so this might sound somewhat familiar to you. So reactant concentration. If I increase the molarity, I'm increasing the chance of collisions that will be effective, and so that can make a reaction go faster. The opposite would be lowering the molarity, and the reaction goes slower. The temperature, we learned a little bit about temperature when we talked about kinetic molecular theory. And so if they increase the temp, then that means the particles have more energy. And since the activation energy is the energy barrier needed for the reaction to happen, this is what will happen. A higher temperature means the particles will collide with enough energy. They're also moving faster, but that's not so much what we're talking about here. We're talking about that they have enough energy to make an effective collision. Surface area is something that we look at if we grind stuff up into smaller particles. So instead of having one big block like a sugar cube, if I had a bunch of tiny pieces, that usually makes the reaction go faster because we can have more collisions instead of only being able to access the outside. And then finally, a catalyst. A catalyst can provide an alternative reaction pathway that will lower the activation energy. So in the body, an example of catalysts are enzymes, and that is a bridge between chemistry and bio a little bit. They will lower the activation energy that will allow the reaction to happen. All right, thanks for listening.